Hi. So I think we'll start now. If others are coming, maybe we'll catch up with a brief summary. So let me start by introducing myself. So my name is Neha Kuntevar, and I am a PhD scholar at IIT Madras. Um, so I'll be the TA for this course on computational complexity. And this is a 12-week course, so we'll have one a live tutorial session once a week. So typically we'll have on Mondays 7 p.m. to 8 p.m. To 9 p.m. And if there are any changes, then yeah, I think you will be conveyed by the mail. So but otherwise, if there's no change, we'll stick to the Monday timings. And yeah, I think yeah, that's all. So yeah, so the topics for today is going to be around the basic complexity classes, uh, the P as well as NP. Then, yeah, so we'll just try to understand these basic classes, what languages fall into these classes. And yeah, I mean, we'll refine this further as and when we come to it, but as of now, let's just keep these two in mind. So what are the, just as a quick recall, what is the class P? It is the set of all languages that have uh, I mean a polynomial time set algorithm, or you can say a deterministic Turing machine uh, to decide the problem. So you have a decision problem, and so the decision problem is essentially you have an input, and you want to yeah you want to check whether say X is in the language or something, and if the answer is um, I mean yes, if say X is in the language, no otherwise. So these are just yes no type questions. You don't have to output a function, or I mean it's just a binary answer otherwise. So this is just the flavor of what these questions are. For example, an example would be whether a graph is a tree. So the input could be graph G, and you want to say yes if G is a tree, and no otherwise. That's it. So there's no computation that's happening, it's just a decision problem. And yeah, based on this we have defined several classes. So
I have a query at this point.
yes.
So can't we model every problem on the planet as a difficult class problem? Like say, if I pose, if a very hard problem is given to me, then I can always pose this problem like, so is 5 a solution of this problem? So clearly, either to say yes or to say no, I'll have to solve the problem. So does this mean that every problem on the planet can be viewed as a difficult class problem?
Okay, so that is a good question. I mean, there's a very nice question. So indeed, there are several problems that we can model as decision problems. These are called optimization problems. So, for example, if you've heard of vertex cover or something, you want to find minimum vertex cover. What you do is, instead of, so the minimum vertex cover is going to be a value, right? It's not a yes or no type answer. But what we do is we formulate that optimization problem as a decision problem by asking. So the optimization version would be um, input is a G, and you want to find the minimum vertex cover in G. So this is a value which is not a binary answer, but you can formulate it as a decision version, which is that you give an integer k and ask whether there is a vertex cover of size k. So this is now a decision problem, and the idea is that we'll keep on changing the value of k and keep asking the question polynomial number of times with the hope that if I can solve this problem, I can solve the optimization problem. So we'll just keep varying the value of k and finally get this answer. But it is not always possible to have this kind of a nice conversion from optimization problem to decision problem. Or even if there is a conversion, it may not be uh, that in polynomial number of queries you'll be able to get to the optimize I mean you ask only polynomial number of times the decision version of the problem, and using all these answers figure out the answer to the optimization problem. So for example, uh, there is this class called um,
మరి ఇప్పుడే స్టార్ట్ నేనేం చేయను
uh, can you please mute? If you're not Jaya. Okay, thanks. Okay, so for example, there is a hierarchy called the functional version of the problem. So these are called FP, FNP, and so on. So this hierarchy goes much above. If you are familiar with the names P, PNP, and so on, it's okay. Otherwise, don't. You're familiar with this, right?
Not much.
Oh, okay, sure. So, okay, then maybe I'll just give an example. I'll not get into the definitions of this right now. So, um, yeah. So, for example, if the question that is being asked to you is, um, so is to find the number of cycles in the graph, or for example to find the number of Hamiltonian cycles in the graph, or and so on. So you can of course think of it as a decision. Okay, so how would you, let's say, if I ask you number of Hamiltonian cycles, let's say this is the question that you want to solve. Okay, how do you convert this into the decision version?
So does it adjust a number of the Ham cycles greater than 50?
Right. So you'll think of the natural way to think of is that you put another parameter k, which is an integer. Okay, but is it necessary that using so for example here the nice thing that we had here is we had a upper bound on the value of k. So you know that k cannot be more than the number of vertices because it's a vertex cover, so it's anyway going to be a subset of vertices. It cannot be more than the size of it. Therefore you could, because you had this bound, you could say that okay, I'll keep on asking over and over again until I find this optimal answer. So this part is fine, right? That we could ask
Yes,
it. Huh.
yes.
But it's not always necessary that the quantity you are looking for is very nicely bounded by polynomial size. It could be that maybe the number of cycles, okay, in this case I'm not sure what the bound is, but yeah, but this k need not be very nicely bounded by n. For example, this could be 2 to the n or something. Then there is no way that you just ask polynomial number of decision problem questions and find uh, the functional answer, the output. So although you can frame it as a decision problem, it may not be useful in solving getting efficient answers.
Yes, thanks.
Okay, good. So okay. So I'll just quickly recall the definitions of P and NP. I'll not give a rigorous definition, but whatever we need for solving the problems today. So P is the class of decision problems that have a polynomial time solution. So there is a deterministic Turing machine that uh, for the language L, which runs in polynomial time. And The only difference with NP is that instead of deterministic Turing machine, you have a non-deterministic Turing machine which runs in polynomial time and gives you the answer to the input. I mean the question. So there are alternate definitions of these, which okay, maybe I'll just talk about one alternate definition of this. So you can think of NP as um, as tossing some non-deterministic coins. So the input to you is x, but it keeps on tossing. So the deterministic Turing machine reads the input, reads the content on the tape, and decides what to do next, to move to the left or right, what to write on the tape, and so on. But the non-deterministic machine has this extra um, power that you can think of it as tossing some coins. So at every stage it decides whether to go to the left or right, and it keeps on doing that, and at the end of it it tosses some p of n many coins, which is polynomially bounded by the input size. So it keeps on doing this, and eventually at this root level it decides whether you're going to accept or reject. So this could be accept, reject, and so on. And the idea is that if any one of these paths, so this is a tree, right? This is a computational tree, and the idea is that if any one of these paths takes you to an accept state, then you're going to accept the. So it's possible that there are several rejects on the way, but if there's one accept, then you're going to accept. Otherwise, if all are rejects, then you're going to reject. So the yeah, so if the computational tree has one path that leads to accept, then we accept, otherwise we're going to reject. And equivalently you can think of this as having a efficient certificate. So efficient and small certificate. So what do we mean by that? So let's take the our favorite NP problem, which is SAT. So the input to us is a formula, or let's say 3 SAT. So you have several clauses, and so on. So you have several clauses like this. Um, okay, and so the input is this formula, and the output is yes if phi has a satisfiable assignment. What do we mean by that? So it just means that if there is a 0 1 assignment to this variable sex size or literal sex size such that the formula evaluates to true, then we say that the formula is satisfiable and no otherwise. So I mean, I'm just going quickly over this because you might have already seen the lectures, but if there's something that I mean, yeah, that you would want me to explain further, then please let me know.
Yes, I have a little query here. That I mean, so I do feel a kind of asymmetricness in between these two definitions. That on one side we are solving a problem using non-deterministic Turing machine in the polynomial time, and
Okay.
then we call the problem belongs to the NP class. And on the other hand, say if the problem is polytime verifiable, then also we say that the problem belongs to NP class. So I mean, but then I mean there is a difference in the gravity of the solution. On one side, we are solving something, and that too by a very, very powerful machine, the machine which is non-deterministic in nature. Whereas on the other hand, we are just verifying the solution. So how can both be equivalent to each other?
Huh. Okay, good. So yeah, so you are right. So you are saying that one hand of this on one hand of this definition, we are saying that sort of has this. There's a non-deterministic machine which tosses coins and looks at whether one of the paths takes you to accept. On the other hand, we are just saying that there's some efficient certificate that you'll just be able to verify. So so why are these two equivalent is because you can yeah, so I'll just tell you. So where is this small efficient certificate coming from? So what do we mean by what is this certificate? It's something that we are guessing, right? So we are saying we'll guess. In this example we have this 3 sat instance, the formula. So the idea is that we are going to guess a certificate, and in this case that certificate is going to be a 0 1 value um, of the literals. So for example, the certificate could look like this, which means that x1 takes a value of 0, uh, substitute x2 with 1 and so on. So this small certificate, okay, and I'll talk about the length and all later, but this certificate is essentially saying that we substitute these values into this formula phi and check. And okay, once you put this 0 1 values, it's just a matter of verifying whether it evaluates to 1 or not. And what this tree is essentially doing is the same thing. So at this point, think of this as telling you whether x1 should take a value of 0 or 1. So there are two possibilities. At the next level, think of x2, think of deciding what is the, we're tossing a coin and deciding, or let's say guessing, what is the value of x2. So it's possible that, let's say, we explored the right branch, so x1 was 1, but for x2 you have further two choices, so it could be 0 or 1. Even if you would have explored the left branch, x2 could be still 0 or 1. So think of every level as guessing the value of each literal. So this is exactly what is happening here. So uh, if I have to trace this certificate on the tree, it will be something like this. So for x1 you chose a 0, for x2 you chose a 1, for x3 it's a 0, and so on. So eventually, because this particular choice of literals satisfies the formula phi, what this corresponds to is that this path will lead to an accept. So in the case of the formula, it's very obvious. This is an obvious interpretation. For different NP problems, the interpretations may be different. So this tossing that we're doing at every point corresponds to a guess that we are making. So so it's just that here we are thinking of like expanded out view and saying that one of it should lead to accept. Here we are just saying that we'll just look at that certificate which takes you to accept. So does it answer the question, or
I would require a little more explanation. So, say if I want to show a problem belongs to NP class, so then what are the standard steps involved? Is it sufficient to show that if you give me the certificate, I can verify whether it's a solution or not in the polynomial time? Is it sufficient to show that the problem belongs to NP, or do we also need to show that look, there are enormous number of the possibilities and therefore I cannot solve this in the polynomial time? However, if you give me the solution, then I can verify the solution in the polynomial time. So what are the standard steps involved in showing a problem belongs to the NP class?
okay? So good. So because these two models, so I did not rigorously prove why these two things are equivalent, but there are two standard ways of showing that a problem is in NP. So if you work with this definition of efficient certificate, okay, and also okay, I guess I did not mention what is this small here. So what the small means is that the certificate that we are guessing has to be of a size polynomial in terms of the input. So in this case, the size of the certificate is just n, which is clearly polynomial in the input size phi, and that corresponds to the depth of the tree here. So I think that this part is this. I'll address your question, but is this part clear that the length of the certificate sort of corresponds to the height of the tree that we.
Yes, that's clear.
Okay, good. So, okay, so if you want to show that language, how do we show that a language is in NP? If we work with this definition of certificates, then the standard thing to do would be uh, is you show is that you show that there is a first thing is there is a small certificate, that is it should be bounded by polynomial, by length polynomial in terms of the input size. Second thing is that it should be efficiently verifiable. So okay, that means if you give me the certificate and given the input using just the certificate that you have given me C and the input say X that I have, just using these two I should be able to decide the output whether I want to accept or not. So that is what we mean by efficiently verifiable. So I should be just using this, I should be able to decide in polynomial time. So these are the two key things. One is the certificate should be small, otherwise you can't even read the certificate efficiently. So forget about using it to solve the problem. So in order to be able to even read the certificate, it should be bounded by polynomial size in the first place. So any decision problem that you give me, if I can show that it has a small efficient certificate, then it is sufficient. So it's sufficient to put it in NP. Or if you want to use the second definition, so there are several examples where it's very intuitive to directly use this definition and just show a certificate which satisfies these two properties. Whereas there can be problems where coming up with a certificate like this is not very intuitive. But designing a non-deterministic Turing machine might be easier. So if you want to prove that a language is in NP with this definition, then what you have to do is is basically you come up with description of the non-deterministic Turing machine for the problem at hand. And what do we mean by description of the non-deterministic Turing machine? The tuple that you have, right? So you have this, okay, yeah, you have this definition of the non-deterministic Turing machine where you have the alphabet, the tape alphabet, input alphabet, the left right movements that you allow, so all of that, right? So basically we will have to describe the working of the non-deterministic Turing machine. So given an input, what are the on this particular configuration, what are the moves and so on. So so typically we generally deal with the first way because it's more intuitive to come up with, but there can be cases where this is a bit difficult, so we do tend to switch between the two, or sometimes it may be that both of them are easy to come up with. So
So where is the difficulty in the method one? Is this to get the certificate? Is it necessary to show the certificate in reality that okay, this is a certificate for this input X, and and for which the verifier will generate the one as the output, or is it sufficient to show in wordings only that okay, so if you give me the certificate, then I can verify the certificate efficiently, and that is sufficient to show that the language belongs to NP?
Okay, so okay, so the um, the thing is that even though we talk at a high level, so for example, in this case of SAT, we just said that the certificate is going to be the assignments to the variables. We did not show how we will come up with it. Okay, so actually we're sort of dealing at a high level here, and we are hiding the details behind it, because eventually what is happening is the equivalent working in the non-deterministic Turing machine world, but because it becomes sort of mechanical, if I mean talking in terms of the function and so on, and uh, therefore we sort of like it's we sort of tend to hide the details and talk about the certificate in terms of we basically write it in English, right? So when I say that I have a certificate, we just said that it's going to be the assignments to it, rather than writing the um, sort of the machine level description of it. So internally that is what is happening, but we'll sort of um, we'll sort of be at a high level and just write English sort of descriptions of what is happening. But even though what is actually happening is, uh, I mean, um, there's a working of what is actually happening there, but we'll not be getting into it.
Yes, yes, I understood. Yeah, thanks. Slightly related point here is that so can you suggest some problems wherein even the verification of the certificate is very difficult? Because this step seems so very trivial that if you give me the certificate, I can easily verify the certificate. So there must be some problem wherein the verification of the certification won't be that easy task.
Okay, good. So I'll talk about one problem that is close to my research area. It's called range avoidance problem. So I'll just talk briefly about circuits. You might have seen this, but I'll just first define the circuit. So a single output circuit here is, you have this AND OR gates, negation gates, and so on. These are connected by wires. At the top, there is an output wire. There are inputs feeding into it. So, I mean, yeah. So it's basically a circuit with AND OR negation gates. There are n inputs and one output. So this is our single output circuit C, but I can also define a multi output circuit C. So we have n inputs and n input wires here, x1 to xn, and think of this as several circuits like this clubbed together, like they're just lying besides each other. So this may be one such circuit, one single output circuit. Its output is y1, but there may be some other circuit like this which takes some other subset of inputs and computes output y2. So they may share inputs and so on. So there are several such circuits, and there are many of them. So is this model clear?
Yes, yes.
Okay. So, um, okay. So the what are all possible inputs that can go in here? So there are n inputs. Each of them can take 0, 1 value. So how many total inputs can there be?
2
If
raised to the power n.
2 to the power n. And what is the total number of outputs that can be there? So assume that m is greater than n. What are the total possible outputs that can be there?
So corresponding to two inputs, we will get, corresponding to at least two inputs, we'll get one output. Is this the case here? Or we can, the circuitry can take multiple number of the inputs as well.
Yeah. So these functions can take any number of inputs.
Oh, I see. So then it would be the power set of the 2 raised to the power n, and the value would be used, I guess, 2 raised to the power 2 raised to the power n kind of.
Okay. So okay, so if I just naively count what are the, so this is basically a tuple, right, y1 to ym, and if I just naively count it, each of the yi's can take a 0 1 value. So this is 2 to the m, like a very bad bound.
Yes.
Okay, but notice that this is basically computing a function, right? So the function is as follows: it takes these inputs, I mean 0 1 to the n, each xi takes a 0 1 value, and it computes a value in 0 1 to the m. But notice that once I fix, let's say I fix an assignment to the xi, so some 0 1 assignment, then the moment I fix it, the value of y1 is fixed, the value of y2 is fixed, and so on. The value of ym is fixed. Essentially, when I fix an input, there can be only one output that it can produce.
I could not understand this.
Okay, so let's say I fix the inputs to some 0 1 assignment. Okay,
Yes.
so the moment I do that, the value of the yi's is also fixed.
Which wires?
All the
wires?
wires, all the output wires, because this is simply evaluating the circuit.
Correct. Yes.
So let's say I look at all zero input assignment here, it will take me to some output. It cannot
Yes.
take me to two outputs. Similarly, each of this assignment here can take you to at most one possible output.
Yes.
Okay, so essentially it's a function. So even though there are 2 to the m possible assignments of yi's here, actually the number of outputs that the circuit can produce is only bounded by 2. It can at most be 2 to the n. It will be 2 to the n if all inputs take you to different outputs.
Right.
Right. So because m was greater than n, there were more output wires than the number of input wires. What happens is this 2 to the m is clearly larger than 2 to the n.
Correct.
Correct. So that means there is definitely something out here which the circuit cannot produce.
Yes, that quantity is 2 raised to the power m minus 2 raised to the power n.
It is at least 2 to the m minus 2 to the n, because it may so happen that, let's say, all the inputs just take you to one
Yes.
single value. So it's a pretty large quantity, and the question is, okay, so what is the question here? The input to us is a circuit C, which is a multi-output circuit here, and this is not in the decision version format right now. I'm just writing the computational format of it. Is to find a y, which is the output assignment, such that for all x, for all inputs, c of x is not equal to y. That means, what does this mean? It means basically we are finding a y here which the circuit cannot produce. That is, no matter what input assignment you give, if when you evaluate the circuit on it, you will never get this y. So basically the circuit avoids y, therefore it's called the range avoidance problem. That is, it's outside the range of the circuit. Is the problem clear? So
Yes. Problem statement is clear.
okay, so this is not in the decision version right now. So if you have to convert it into decision version, how would you do it?
So, like in this case, whether the Cx is so I can say that whether so is there is the range same as the input or not, right? So is there a hollow space I mean in the codomain or not, right?
Yeah.
So that is an variant of this.
Yeah, or okay, Okay, in this case, it so happens because m is greater than n, we are certain that there is definitely something here outside because of the combinatorial argument that we did.
Yes, yes.
Okay, so one probable decision version would be I give you the circuit and I also give you a y, and you say yes if y is in the range of the circuit. That is, there is some input assignment which will take you to it. Okay, so can you come up with the uh, certificate for this?
Okay. So So input is C, and C is a given circuitry. C is the given
C is
circuitry.
the given circuit.
Yes, and okay. Uh, so now I mean, so if I give you any assignment, I mean, then we would be able to check whether uh, this is there in the range of the circuitry or not. We would be able to check in the polynomial time, isn't it? So if you give me any certificate, then I would be able to show that whatever output I get belongs to the range of the circuitry or not.
Hmm.
Answer of yes is obvious.
Hmm.
And what about no? So quite possible that will I get the answer of no as well? Yes, I will get the answer of no as well if y is not there in the range of the c. So yes, this is, I don't know what did I tell you, but it seems that as if the problem is decidable kind of a thing. However, for the NP thing, for yes, we should get the answer, and then for the no thing, you keep on giving me the certificates, and every time I'll get the verifier will generate the zero as the answer.
Okay, so okay, I agree with half part, the first half of it. So let's say this is the decision problem that I'm working with. Then, uh, then how will you convince me that the answer is yes? You will give me the input. So the certificate here would be you give me the input x, which is the assignment, and what I'll do is I'll simply evaluate the circuit on this particular input and check whether it produces the y that was given to me. So this is efficiently verifiable because I'm just computing the circuit, and it's also small because it's polynomial in the size of circuit. So this problem is in NP, but the moment I change this, because what I'm interested in was something that is outside the range, not something in the range. So if I change this slightly to just by flipping the yes or no, so I'll say yes if it is not in the range and no otherwise. Then can you come up with the uh, certificate?
So in this case, it would be it won't be possible for me to check that whatever input I gave, whether whatever it generates, quite possible that it may belong to. So it does not belong to the range. It's okay. It's okay. So it would be difficult for me to get such a certificate. But then, this is just like that. This time, it is difficult for me to verify yes, but then probably would be easy for me to verify no. And however, in the previous case, it was easy for me to verify uh, yes and difficult to verify no. And so in this case, the coin has just flipped, and probably the nature of the problem, uh, I mean, probably remained the same. Nature remained the same in the sense that probably this could be an instance of co-NP and not NP. So some kind of asymmetricness is here. But my query was slightly different. That can be come up with a problem wherein even the verification of the certificate, even for the yes instance, is very difficult, because certainly there are problems which are tougher than the NPN complexity class. In that sense, I was asking that query.
Okay, so you okay, I get it. So your question is even yes as well as no is difficult.
Not no, but yes. Say let us stick to yes thing only. So the yes
Well,
thing is difficult.
well,
Yes is difficult, but then this should not be the co-NP problem, because then
no
I
would be
mean,
difficult. I mean, if it's a co-NP problem, then no is verifying no is easy, but if it's an NP problem, then verifying yes is easy. So you are essentially asking something that's above NP as well as.
so probably I am. So my query is if I can if I can explain it well, then even the I mean of finding the needle in the haystack is even is difficult. I mean, as if as if verifying the certificate becomes similar to finding a needle in the haystack kind of a thing, that there would be so many possibilities to check, enormously large number of the possibilities to check, that even the verification of the certificate becomes so difficult. There might be or must be some situations like this also.
Um, yeah, so, okay. Okay, so if you, um, I mean, so if you take, um, okay, let me come up with a good example.
Or you can continue with the the next set of the questions, and probably this thing will come in the during the session. Probably we can or then you can show such an example, because my only query is that uh, verifying certificate seems to be so trivial. And can we think of something wherein even verifying certificate becomes so very tedious?
Yeah, so, okay, so I'll just, okay, I'll, if I come up with the example, maybe I'll tell it now, but, okay, but you're familiar with the class NP and co NP, where here verifying yes instance is easy, and here verifying no instance is easy. Okay, now there is a hierarchy above this which says that even if I were to, even if someone were able to give me a magical, let's say, solution to the SAT problem, okay, or any NP problem for that matter, even if I had access to those answers, so I have free answers to it, I can ask as many times as I want. So let's say I have to solve some problem, I'll need to there's some magical machine which we call Oracle, but I mean we'll get into it all this later. But let's say I had access to such a magical path. Even with access to it, can I solve the current problem easily or not? Okay, so that is that is one more level of hierarchy that we're building. Even with access to these solutions, can I solve those questions or not? So these are this is called sigma 2p. Similarly, you have pi 2p, and I mean there is a whole lot of hierarchy that um, yeah, that goes on. This is what we call polynomial hierarchy. And okay, and what do we mean by, I mean, yeah, what we basically mean by this is, even if I were to have a solution to these NP problems, even with that, finding answer to this is difficult. So for all these problems above, we do not have an easy way of verifying. So there are definitely, I mean, problems that are out here, but I may not recall the exact definition, but I'll just give you some pointers. So take, okay, I mean all of this will come up later, but if you are interested, I'll just Uh, yeah, I'll just write the problems. You can take a look at it. Um, okay, so this is there is a VC dimension problem. Okay, and there are several others, like for each of these classes there are problems. Some of them are very natural, some of them are more mechanical or more mathematical. So those are the problems of the kind, for example, if the input to you is a Turing machine, uh, then you want to say yes if uh, if it always halts in polynomial time. So you want to verify this, whether it always halts in polynomial time or not. So there are several natural graph problems such as the king tournament and so on that naturally fall into these hierarchies. There are problems of the other kind that I mentioned. Given a machine, you want to check this particular property of it. So for those instances, you don't have a natural easy certificate. So I don't have an exact question right now, but I'll maybe will get into it later. But I just want to say at the moment that there is a there is indeed a hierarchy up above where verification is very difficult.
Okay, yeah, thanks.
Okay, so okay, I'll just start with simple questions today. Um, yeah, this maybe we'll see. I mean, based on time, but we'll just start with simple questions right now. So okay, so for each of the questions, okay, maybe we'll just take a look at the first part. So use okay, for each of these questions, we'll try to show it's in NP and in P later. Okay, so first maybe I'll just read out the question. So you say that a graph is connected if between any two vertices there is a path. So we'll define a language called connected, which is the set of all graphs G such that G is connected. And the decision version is given input G, check if. So this is a membership problem, and let's say you want to show that this problem is in NP, then how would you come up with what would be a certificate?
So certificate would be that can you scroll it up so that I can see the problem statement? Yeah. So certificate would be that set of the vertices, but then along with the set of the vertices, I would also be requiring some information about the graph, that for which graph these two vertices are given, because the connected is the collection of all the graphs and which are the connected ones. And then I can use, or in fact, we do have polynomially time efficient algorithm to find the strongly connected components. And which runs in an effort of the order of p plus e, of the order of p plus e. So it won't be difficult to check that whether, a particular graph is connected or not. Now the remaining question is that this language is a collection of all the graphs. So what would a certificate be? So certificate would be a set of the vertices and along with some information about the graph.
Yeah. So yeah, good. So in this case, I mean you're right. So first of all, the problem is in P because there are efficient ways to check whether a graph is connected. Um, which is that you can run either of the BFS DFS algorithm, which runs in order size of V plus size of V time, which is clearly polynomial in terms of the input size. So we can run this algorithm and check whether the graph is connected or not, and that itself gives us a polynomial time solution. Now if I want to show that the problem is in NP, I'll have to show that for every pair of vertices there is a path. It's not for some pair of vertices. So most trivial obvious thing to do here would be you choose all possible pairs of vertices. So there are n vertices, there are n choose 2 pairs of vertices, and let's say I give you one such pair. Then what would be the certificate? It would be a series of vertices, right? Some I mean, these are not necessarily, yeah, some series of vertices that eventually lead you to V. So this is a path. And what is the size of this path? I mean, rough bound.
So, uh, but then, so size of this a particular path would be bounded by the number of the vertices in the given graph.
Right. So this is at most n.
Yes.
Okay. And how many pairs are there? For one pair, the size of the certificate is of size at most n. There are only n choose 2 pairs, which is roughly n square. And for each certificate, for each pair, we are spending at most n uh, length for I mean size further. So this certificate, so it's basically uh, I mean yeah, we're basically writing uh, all these paths one after the other, and yeah, so altogether this would just be mm, order n cube. Is this okay? I mean,
Yes, but then somewhere I need to mention graph as well. That for which graph, because the language is a collection of the graph, for which graph this sequence will result into a connection.
okay, yeah. So the input to you is
Oh, I
a
see.
graph G, right?
Yes.
Because if this were a language, then the input to us is an X, and we want to check whether X is in L. This corresponds to whether X is in L.
Yes, yes, right.
Okay, so good. So yeah, maybe we'll just do one more. Yeah, one more problem. Maybe we'll do B. So same thing. You want to come up with a certificate and an algorithm.
So, how to show that a graph does not contain a triangle or does contain, so a triangle would be formed if I should be able to traverse to the same vertex, and but then the length of the path should not be more than 1, 2, and 3. Should not be more than 3. So yes, basically I need to find. So if a graph is given to me, then I need to find. I need to show a certificate that there does not exist a sequence, uh, a sequence of the length 3, and wherein the start and the end points are same in that graph. So if that is the case, then the graph won't be containing a triangle. And this can be done in the polynomial time, I guess, because yeah, we can use a DFS kind of algorithm while also maintaining the length of while also maintaining the intermediate vertices vegetate, so that we can keep the track of the length of the path.
Yeah, you can modify the algorithm and yeah, and check for triangle. But also, a very simple, a very naive idea would also work in this case, which is that you just go through all possible triplets of vertices. So there are n vertices, and there are n choose 3 many triplets of vertices possible. For every triplet UVW, you just have to check whether UV forms an is an edge, VW uh, is an edge, or I mean, just check whether they form a triangle. This is not ordered, so it could be any, um, I mean, in any order, but yeah. So this just these three checks can be done in order one time, and there are n choose 3 many triplets. So altogether, the algorithm basically just goes through the triplets and check whether they form a triangle. So this can also be done in order n cube time. So this gives you a polynomial.
Yes.
Yes, and the same thing can be extended to give you a certificate. Certificate is just going to be um, a join of all these, um, all these triplets.
Yes. Yes.
Okay, good. So I'll skip the other two maybe for now. I'll move on to the next question. Um, okay, I'll maybe we'll do this first because okay. So I'll just yeah, recall the problem. So the SAT that we saw, which is NP complete problem. Okay, what do we mean by NP complete problem? We have this class NP, which is the set of problems that have efficient certificate, a small and efficiently verifiable certificate, and we have the class P here, which is sitting inside, because if you can solve the problem efficiently, then of course you can verify it efficiently. And then there are some hardest of problems in NP, which we call NP complete problems. What do we mean by that? For all the problems in NP, L reduces to L prime in polynomial time. So this is the notion of reduction. So if you would want me to recall, then let me know. Otherwise, I'm assuming that yeah, you've seen this. Then you say that L prime is NP complete. So what it means is, it in some sense, L prime is one of the hardest languages in NP. If you could solve L prime, then you can solve all the other problems in NP. That is what this means. Okay, and there are several problems here. The first problem that fell into this, that we came to know of, was 3 SAT. Then there are several other problems like vertex cover, independent set, and many, many more that fell into this category of NP complete. Yeah. So, so this SAT is, as we saw earlier, is that the input to us is a formula in 3CNF. Okay, I'll not get into the 3CNF, it's just a formula. And output yes if phi has a satisfiable assignment. And no otherwise. And now we are modifying the question slightly to define a new problem called double SAT. Which means that the input is a formula and you're going to say yes if phi has. So the only difference is here you needed one satisfiable assignment was enough, Here you want at least two satisfiable assignments and no otherwise. So the first question is whether double sat is in NP.
Yes, so double set, yeah, would be the element of NP, because if you give me certificate, then I can verify whether I'm getting at least two. So basically, you would be giving me two satisfying assignments here, and I can verify them efficiently.
Yeah, exactly. So you will guess two assignments, check whether they are different, they are not equal, as well as both of them satisfy. So this is clearly in NP. And is this also NP complete?
So then I'll have to reduce some existing NP-complete problem into this double set, and the natural choice probably would be to go for satisfiability one. But if I reduce, so how can I rephrase each and every instance of the satisfiability into an instance of the double satisfiability? Because for the satisfiability, I just need only one assignment. But then here I would be requiring two assignments. So probably if I can make some modification into an instance of the satisfiability problem by using some or operation or something, so that whenever I have, I don't know how to do that. But yes, but the question is that how to rephrase each and every instance of the satisfiability into an instance of the double satisfiability.
Yeah, yeah, exactly. Uh, so yeah, what we want to show is that satisfiability reduces in polynomial time to double sat. That is, the input here is phi, a formula phi. I'm going to do some surgery on it and come up with another formula phi prime such that phi has a satisfying assignment if and only if phi prime has at least two satisfying assignment. So this is exactly spot on. So this is what we want to do. From one instance of satisfiability, we want to convert it into an instance of double satisfiability such that this property holds. Okay, so what is a uh, natural way to do that? Um, okay, I'll just maybe. Okay, so I'll just. I mean, there are several other. I mean, ways in which you can come up with this. This is just one way of doing it. So maybe one thing that we can do is I can define phi prime as follows. So this phi, and I'm additionally introducing two more variables. So let's say x1 to xn were the previous set of variables. I'm going to introduce two more variables, xn plus 1, xn plus 2, and add the following clause. Okay, this is not exactly a clause, but okay, and this is essentially xn plus 1 bar and xn plus 2, or okay, so we need not worry about bringing this into the 3 sat instance or something, because the input instance to us was um, yeah, was just any formula phi. It was not in the 3CNF form anyway, so we need not worry about bringing this into that form, although it's not very, may not be very difficult. So uh, this is a small modification that we've done to the original formula. So can you see, maybe make some observations about this?
Yes, so whenever phi has a satisfying assignment, so I can always augment that assignment with something so that the second Boolean expression also comes out to be true. And that can be done because, because this and is being used here, so both the Boolean formulas should be true simultaneously. And so I need to pick the values of xn plus 1 and n plus 2 such that, I mean, this odd Boolean expression comes out to be true. And this can be done. This can be done.
Yeah, so what we're essentially doing is whenever you have say one satisfying assignment for fee, I can use, so let's say, um, I mean, x1 to xn, this is some assignment A that's going to um, satisfy the formula phi. What I'll do is I'll substitute xn plus 1 with a 0 and xn plus 2 with a 1, so that this particular expression evaluates to true, and therefore this whole expression evaluates to true. So I've got, this gives me one assignment, one satisfying assignment for phi prime. At the same time, what I can do is I'll use the same assignment for x1 to xn that we used earlier, but this time xn plus 1 is 1 and xn plus 2 is 0, so that this expression evaluates to true, and therefore this whole expression evaluates to true, and hence phi prime is true. So this gives me another assignment, satisfying assignment for phi prime, and clearly these two are different assignments because there is a variable where both of them take different values. So clearly both the assignments are different, and therefore if there is one satisfying assignment for phi, we are able to produce at least two satisfying assignments for phi prime. In fact, if the number of assignments, satisfying assignments of v is k, then there are exactly 2k many satisfying assignments for phi prime. So I mean, that's just yeah, an observation. And so therefore what we've got is, if phi has a satisfying assignment, then phi prime has at least two satisfying assignments. And what happens if phi has no satisfying assignment?
I have the, so if we does not have any satisfying assignment, so neither this would be having the satisfying assignment because we are using and here.
Exactly, yeah. So if this part itself is never true, then a conjunction of it with anything will never be true. So then phi prime also does not have a satisfying assignment. Okay, so yeah, so that proves this this uh,
So I have a little doubt here. I mean,
yes, yes.
when you use the bidirectional implication, because if x is the element of L, then I can find a transformation wherein f of x belongs to L prime C. If I'm trying to reduce L into the L prime polynomially in the polynomial time. So
Okay.
like say if x is an instance of the satisfiability, then the f of x would be the element of the double satisfiability.
Okay.
But is this necessary that this transformation should be bidirectional? So is this necessary that whatever transformation I find to rephrase an instance of a problem into the as an instance of the other problem, then such a transformation should be bidirectional?
Okay,
I
so
mean, if I can reduce each and every instance of L into an instance of L prime, then it is necessary that I should be able to reduce each and every instance of L prime into an instance of the L.
huh. Okay. So okay, good. So the thing is, you want to, okay. So are you actually asking that if A reduces in polynomial time to B, then does it imply that B reduces in polynomial time to A?
No, this is not necessary, because if A is getting reduced into B, then the problem B is at least as hard as the problem A is, and nothing can be said the hardness of the problem B. So
Yeah.
clearly, this B, I mean, this inequality, I mean, this right hand side need not to be true.
Need not
That
be
is,
true. Yeah.
yeah. But
So
my query is slightly different when you use the double implication thing here. That phi has a satisfying assignment. Probably you wanted to say if and only kind of thing, or what?
yeah, so we mean if and only if um, because one direction is not enough. Why is that? Because what we're saying is, when I say that I reduce satisfiability to double satisfiability, what I mean is it is enough for me to solve this question, this problem. If I can solve this problem, then I can get a solution to the satisfiability problem. So how is that happening? We're saying that if the answer to phi prime is a no, then the answer to phi is no, and if the answer to phi prime is a yes, then the answer to phi is no. So that uh, I mean, both the directions are needed, because otherwise I'll only be correct in one of the scenarios. Say if phi is satisfiable, only then I'll be correct, and if say, or I mean, it can happen for either of the two conditions, but not for both. But I want to solve this problem irrespective of whether the unconditionally, right? So therefore you need both the directions, because yeah, if the answer is no, then I have a solution for double sat which will tell me the answer for this is no, hence the answer for the other one is no. So it's not necessary that a no here, in this case it so happens that the yes of this translates to a yes of sat. That is, if uh, there are at least two satisfying sorry, that is, there is at one satisfying assignment for phi, then yes of here translates to yes of the other problem, and a no here translates to a no. That is something that happens in this particular problem, but it can also happen the other way around. So in some problem it may swap. But if, let's say, I did not have this part of the argument, and only this were true, then can you say that you have solved sat?
Oh, yes. So what I understood from this discussion is that if X is the element of the language L, then f of X should belong to the language L prime. And if X is not the element of the language L, then f of X should not belong to the L prime. Yes
Exactly.
should map to yes, and no should map to no. Then the problem L is getting reduced into the problem L prime. This is the meaning of this discussion.
Yeah, so what happened in this case is that x in L, if and only if sigma of x, which is f of x, is, I mean, okay, let's say f of x is in this other language L prime, but um, I mean, what I'm saying is there can be situations where a yes here maps to a no, and a no here maps to. It's just a matter of one negation. So, uh, I mean, yeah, um, it's just that both of these should have some function of the answer for the other language. I mean, it's just that you should have something corresponding to a yes here and something corresponding to a no here. It may be flipped, but that is fine.
Oh, so probably I need a little clarification here, because what I understood so far is that if X is the element of L, then f of X is the element of L prime, and if X is not the element of L, then f of X is not the element of L prime. Is this correct?
Yeah, yeah.
Okay, great. Yeah. And I have one related query that if, so just now you told that this NP complete is a representative problem of the NP class, and probably set was the first problem which was proved as NP complete. So then what about the P complete thing? And which problem was initially proved as P complete? Do we have something as P complete or not?
Yeah, so good. So there is indeed a problem called circuit value problem, CVP, and this problem happens to be p complete. So I'm not sure if this is the first that was that was defined or so, but um, okay, so maybe I'll first define the problem. It's very simple. So the input is a circuit C. We just discussed this is basically AND or negation gates connected by wires. So say there are n inputs and this is a Boolean circuit, and the output is also Boolean 0 1. So just a second. Okay, so so the input to us is a Boolean circuit C and uh, an assignment of x1 to xn. So let's say I'll call it a1 to an. This is a 0 1 assignment. Okay, and the output is going to be the value of the circuit on that assignment. So whatever this assignment is, we'll evaluate the circuit and output that. So I'll just say y, which is the output of the y is nothing but c of a1 to an. So yeah, so this is the simply defined problem called CVP. And can you tell whether the problem is in P?
So actually this problem statement is not that clear. So as an input, a circuitry is given along with the input, say A1 to AN, and the output is just one thing, one number. Is this the problem?
Yeah, this is the problem.
Okay, I see. Yes. Yes. Um,
Yeah, and this y is evaluation of the circuit on the input.
and what is the depth of the circuitry here? What is the depth of the circuit?
It does not matter because the circuit C is, you want to run in polynomial time in terms of the size of the circuit. So
Okay. So then for every operation, I will be requiring the constant amount of the time, and if the depth or the height of the circuit is polynomial, so then everything can be done in the polynomial time. So this belongs to the class B.
exactly, good. So this problem is indeed in P. Now, in order to show that the problem is P complete, we'll first need to define what do we even mean by P complete. Right. So, um, So, what is your, what is your guess for the what would you call P complete?
Yes. Yeah. So because I was thinking that if I multiply n cube by another polynomial, the result would again be a polynomial. So whatever transformation I carried out over an instance of a problem and which is solvable in the polynomial time, so whatever I get would be an instance and which can obviously be solved in the polynomial time. So it seems that as if all problems which belongs to the class P can be reduced to any problem in the P class in the polynomial time. So therefore, any problem in the P class can be viewed as is in fact is P complete.
Good. So, okay. So, if we define P complete as follows, that let's say this is our definition one, that we define a language L to be P complete if all the languages in P reduces to L in polynomial time, then you are right. So because that way with this definition you could always convert any L prime into reduce any L prime into L and solve L in polynomial time and get back your solution to uh, L prime in polynomial time. So that way any language L would be NP complete. So with that in mind, so there are actually two exceptions here, but okay, so there are two corner cases that are cut down, but I'll get into it later. So with this definition, it so happens that any L in P is NP complete. So actually there are two corner cases.
NP complete or P complete?
Sorry, thanks. Yeah, P complete. There are two corner cases, but I'll not get into it because at the moment I'll not get into it because I want to make a different point. So, yeah. So if we were to define NP complete, um, okay, maybe I'll okay. So then it does not make sense to even call something P complete, right? Because anyway, everything that is here is also P complete. So it would not make sense for me to even define a class called P complete, because we'll only define when we see uh, some kind of a hierarchy or some properties that something satisfies, but the other thing we don't know or does not satisfy. So whenever we define reductions, this P here is always it should be finer than the notion of the class that we're talking about. So for example, if we were talking about NP completeness, then we are talking about this language in NP, and P is a subset of NP. May not be proper subset, we don't know, but it's definitely a subset of NP. Therefore it makes sense to talk about something finer, some finer notion of reduction. Whereas if I'm talking about P, L being in P, then it does not even make sense for me to talk in terms of polynomial time this being P. So what I'll need is something finer than P, something small. Maybe I don't allow you to do it in polynomial time, the reduction. I'll put further restrictions. So okay, so one such restriction is maybe that if you are familiar with L and L, all these classes, log space.
Yes.
Okay, so I can put several such restrictions and define a different notion of reduction. So instead of this did not fetch us anything because then P was equal to P complete. Therefore, I need a smaller notion, so something smaller than P. Okay, and there are different notions. There's no such thing as right or it's something that we chose to do. So if let's say I choose this particular notion, then this would be coarser than if I choose L. And even there are things below this, you can even choose NC and so on. We'll not get into it, but yeah. So let's say we stick to this definition, then then you can think of classifying something as P complete.
So does this mean that we are looking for a transformation which runs in logarithmic what? Logarithmic space or what?
Yes. So whenever we say L, we mean logarithmic space.
So if something is running in the logarithmic space, would require the linear amount of the time, isn't it?
Yes, true. Yeah.
So then basically we have so we put a restriction over the polynomial that okay, at the most it could be a linear function. So we should be able to transform an instance of a problem, P class problem, into another P class problem in the at most linear amount of the time.
Okay, linear. I wouldn't exactly say linear because this could be say 3 log n amount
so
of.
so then the time would be 2 raised to the power say 3 log n, and then this value again will came out to be n cube then, polynomial.
Yeah, it would be polynomial.
Yeah. So then what benefit are we drawing here by imposing this constraint that this transformation would be carried out in the logarithmic space? It is as good as we could have said that okay, we would be using a transformation which runs in the polynomial time.
Huh. So one thing is we had this. Okay, I'll just draw this figure again. So you had this NP, you had NP complete, and then there was P here, which we don't know whether it is equal or not, but at least it's subset. So when I have to define notion of putting something from this bigger set into uh, a harder set here, I'm using a notion which is uh, possibly smaller than NP itself, which is P. So I did not allow you to do a reduction in NP. Otherwise, everything would have become NP complete, and there would not be such a hierarchy. Similarly, if I have to classify something in P and I want to put it into a harder class, then I'll have to look at something inside P, which could be NL, which could be L. So whatever you choose, that would, uh, the final class you choose, the more and more, um, the richer and richer hierarchy you will get. So, okay.
Yes, I understood this thing, yeah. And this diagram is so very illustrative, yeah. And it says a lot, yeah. Yes.
Okay, good. So actually you can show that this CVP, you take any problem in P, and in logarithmic space you can convert that problem into the CVP problem, such that if you can solve CVP, then the if and only if thing that we discussed, then you would have a solution to L. So in that sense, CVP is a P complete problem, and this is by far the most well studied P complete problem. But it's not necessary that you define with respect to this notion. People have also studied um, the hierarchies within P based on several other notions. So,
Yes, thanks.
okay, actually, today's the first sessions I was planning to cut it shorter. Um, so, is it okay if we stop here?
Yeah, sure, yeah, it's absolutely fine,
Okay.
yes. And all the sessions would be conducted on Monday only, yes.
All the sessions would be conducted on Mondays. That is the plan. But I have a travel for conference that is coming up. So there may be one or two reschedulings that can happen. So I'll let you know personally also. The last time there was some um, communication gap that happened during the announcements. But if there's any change, I think I have your mail. I'll let you know.
Yes, thank you so very much. Yeah.
Okay.
Thanks,
Okay.
and
Okay.
bye.
So one more thing. So this sessions are recorded and this will be uploaded on the YouTube. I think you'll probably get the link through mail.
Yes, that would be nice. Thank you. And
Okay.
please share these notes as well if you can.
Yeah. Sure.
On my mail ID. Yeah, I will
Okay.
mail you and then please share these notes.
Okay. Sure.
Thank you so very
Okay.
much.
Thank
Thanks,
you.
and
Thank you. Okay.